Earlier in the course, we looked at the idea of the energy changes that happen when substance is heated or cooled using the equation Q equals ms delta T. Now we want to look at what happens when a phase change occurs, when something goes from solid to liquid, liquid to gas, gas to liquid, liquid to solid, or even the sublimation deposition phase changes. When a phase change occurs, generally what happens when we're adding or removing heat is that we change the kinetic energy of the molecules, that they speed up or slow down. So when the kinetic energy is decreased, the molecules move slower, and then these intermolecular forces we're talking about can actually cause the molecules to bond together, not bond, but actually associate together, be held together by the intermolecular force. When kinetic energy is increased, the particles move faster, and any intermolecular forces that are holding the particles together can now be overcome. When we look at a change of state diagram, what's happening is we're looking at the temperature versus the time over a process takes place. So when we apply heat to something, the average kinetic energy increases and the motion increases. However, when we hit a point where a phase change occurs, like the boiling point, the temperature remains constant and the average kinetic energy is constant. Molecules are being changed from solid, liquid to gas, and the potential energy of those molecules is changing. Once all the molecules have been converted from that liquid state to the gas state, then heating causes the temperature to continue to rise and an increase in kinetic energy. So the diagram that we see looks something like this. You have a section at the very bottom in black where the substance is heating up as ice, as a solid. This is for water. Then that purple section, it reaches the melting point of ice at 0 degrees Celsius. The temperature remains constant. You get that flat section of the graph. The blue section is where you're heating up liquid water from 0 to 100. Once it reaches 100, the phase change from liquid to gas occurs, and you get another flat section where the temperature remains constant. You're changing the potential energy of the particles. And then once it all becomes steam, the pink line, you can start to heat up that steam again. The slope of those lines is actually based on the specific heat of ice versus water versus steam. The length of the purple and green line is based on the fact that it takes a lot more energy to change from liquid to gas than it does to change from solid to liquid. Solid to liquid, all we're doing is weakening the intermolecular forces, allowing the particles to move a little bit further apart. Going from liquid to gas, we have to completely separate the particles and get rid of all the intermolecular forces. Heat of fusion is the amount of energy it takes to cause 1 gram of a substance to go from solid to liquid. Now remember, on that previous graph, we have these sections here where it is flat. Now if you have a flat section of the graph, you can't use Q equals ms delta T. Q equals ms delta T requires a delta T. So for that to happen, you need a changing temperature. So we can use that equation for the steam section. We can use that equation for the liquid section. We can use that equation for the solid section. But we cannot use that equation for the 2 flat sections. The equations that we will use are based on the heat of fusion and the heat of vaporization. So in this section, we're going to use Q equals m HF, mass times heat of fusion. And in this section, Q equals m HV, known as heat of vaporization. So heat of fusion, the amount of heat needed to cause 1 gram of a solid to melt into its liquid phase. Heat of vaporization is that liquid to gas transformation. It's the amount of heat needed that must be absorbed to vaporize, change from liquid to gas, 1 gram of a substance. For water, here's all the thermal energy data. So the various values that you have for specific heat capacities of ice, water, and steam, and heat of fusion and heat of vaporization, both in calories and joules. We'll refer back to these on tests and quizzes. You'd be given these. So let's look at a sample problem. How much energy is required to raise 15 grams of ice at negative 15 to 75? I think the easiest way to start these is to draw a graph. You need to draw that graph, put on the appropriate points. So water, starting at negative 15, going to 75. Now, you have to ask yourself, are there any phase changes that occur between negative 15 and 75? The answer is indeed yes, there is one at 0. So this graph would look up, flat, up. There are 3 sections to this graph, so we're going to have to do 3 separate equations. Section 1, we'll use Q equals ms delta T. Section 2, we'll use Q equals mHF because it's melting. And section 3, we'll use Q equals ms delta T. Now for each of these, Q, mass, 15. Now we need the specific heat of ice. So we go back, specific heat of ice. It's 0.486 calories or 2.03 joules. Let's do joules, for example, this case. So we've got 2.03. And the change in temperature is a final temperature of 0, an initial of negative 15. So 15 times 2.03 times 15, which comes out to 456.75. Now we need to do Q equals MHF. 15 HF for water is 334 joules per calorie. So 15 times 334, 5,010 joules. This last one, Q equals 15, specific heat for water, we already know, 4.184. And now the change in temperature is going to be final, 75, initial 0. So 15 times 4.184 times 75. 4,707 joules. Now to get the final answer, we'll add those three numbers together. We get 10,173.75. I would keep this at two significant figures because of the 15 grams, or 15.0 grams, so three significant figures. So 10200 joules. Okay, one more problem. How much energy is released when 25 grams goes from 115 to negative 25? So once again, draw a graph. Start at 115. It's our high value. Negative 25 is our low value. Then we know there's two phase changes that happen in the middle here, 0 and 100. So it's going to drop, flat, drop, flat, drop. This section has 1, 2, 3, 4, 5 pieces, so we're going to need 5 equations. Q equals ms delta T for the first section, which is 25.0. Specific heat for ice, or for steam, is 2.00 joules per gram degree Celsius. You could just as easily do calories. And the change in temperature here is going to be 100 minus 115. So 25 times 2 times 15, we get negative 750 joules are being given off. The negative meaning is being given off. Now we're going to do MHV, since it's going from liquid or gas to liquid. Now in this case, the heat of vaporization is 2,257 joules per gram. And it's being lost, so I'm going to make that negative. Which comes out to 56,425 joules. Section 3, Q equals ms delta T. It's a diagonal section, so we'll use the ms delta T. The temperature is changing. Specific heat, 4.184. And delta T of negative 100. So we get negative 10,460 joules. Q equals MHF, 25.0. The HF, 334 that we saw in the previous problem. And it's losing, so we'll make that negative. 8,350 joules, and 5 Q equals ms delta T. We get 25.0 times specific heat of ice, which was 2.03, times a change in temperature now of negative 25. We get negative 1,268.75. Now we'll add all those together. And we get Q equal to negative 77,253.75, and Q equals negative 77,300 joules. Okay, so those are example problems of when we have a phase change.